Okay, today we're going to talk about the work energy theorem. So first I want to remind you, right, you might recall that the force times some time interval, right, we defined as the change in momentum, right?
Yes.
This allowed us to write that the force was equal to delta P over delta T. So the change in momentum divided by the change in time was equal to the force. And of course that force by Newton's second law is equal to the mass times the acceleration, right? So in the event that F net was equal to 0, or no net forces acting on the system, right? That means that the mass times the acceleration is equal to 0, but it also means that delta P, delta T is equal to 0, which means that delta P is equal to 0, which means that P before is equal to P after. Right? Because delta P is defined as, delta P after minus delta P before, right?
Yes.
And so this was the conservation of momentum that we saw before. Okay? So instead of starting with force times delta T, now we'd like to think about force times delta X. Okay? Where delta X is a displacement. Okay?
Okay.
So Newton's second law says that F is equal to m times a, right? F net, really, if you want to be technical about it. And so if I multiply both sides by delta x, I'll get F times delta x is equal to mass times acceleration. But I'm going to write acceleration as delta v over delta t, the change in velocity during some time interval. And of course I have to multiply by delta x on this side as well. Correct?
Yes.
Now, delta v would be equal to some v final minus v initial. That's the change in velocity, yes?
Yes.
So I can rewrite this as mass times v final minus v initial. And also I'm going to take the delta t and algebraically change places. So I'm going to write delta x over delta t, like this.
Okay.
And you might remember what delta x over delta t is from kinematics, right?
Yeah. Let me think. No.
Displacement divided by delta t.
Oh.
What is that equal to?
Over delta t. That's velocity.
Velocity. In particular, it's the average velocity, right?
Yes.
Because these delta x's are larger distances, right?
Yes.
So it's not the instantaneous velocity that we have here, it's the average velocity that we have. And remember that the average velocity, right, the average, which is equal to delta x over delta t, right, is also equal to v final plus v initial divided by 2, right?
Yes.
That's how we would compute the average velocity. So if I rewrite this as mass times v final minus v initial, and I'm going to rewrite this as the average velocity, which is v final plus v initial divided by 2. Right?
Yes.
And let's remember what the difference of two squares equation was. Do you remember that?
Where's yes.
It says that a minus b times a plus b is equal to a squared minus b squared, right?
Yes.
Well, here's my a, here's my b, right? So I can write this again as mass. I'm going to write it like this. I'm going to write it as 1/2 the mass, just to get that factor of 2 out of there, times the quantity v sub f squared minus v sub I squared, where this is equal to vf minus vi times vf plus vi, right?
Yes.
On the left-hand side, I still have f times delta x, right? Let me just rewrite this a little bit differently. F times delta x is equal to 1/2 mass v final squared minus 1/2 mass v initial squared. And you might recognize these two terms as the kinetic energy, or the oomph, that we talked about in the last lesson, right?
Yeah.
And I think we talked about it in the lesson before that as well. So what this says is that F times delta x is equal to delta Ke, the change in the kinetic energy. Okay?
Okay.
And so in a situation where our net force was 0, for example, right?
Yeah.
Like when we did the collisions, the elastic collisions the other day, in the last lesson, there was no net force acting on our constant velocity balls that were colliding, right?
Yes.
That would say that delta KE, the change in the kinetic energy, is 0. So I could say that the kinetic energy before is equal to the kinetic energy after, right?
Yes.
And that's how we solve these collision problems, right? From that we glean, in conjunction with the conservation of momentum, that the relative velocity of approach will be equal to the negative of the relative velocity of recession, right?
Yes.
So that's what we did there. But in general, right, we've got this term here, which we call work. I ran out of room here. And this term here, which we call, kinetic energy. I'm not going to relabel that, or really the change in the kinetic energy. So this is the work energy theorem. It says that the work that you do on a system will be equal to the change in the kinetic energy of the system. Okay?
Okay.
So in the elastic collisions that we talked about yesterday, we didn't do any work because the kinetic energy didn't change, right? The kinetic energy before was equal to the kinetic energy after. But in general, if you do work on a system, then there will be a change in the kinetic energy. So I'll write this up here. Actually, I'll write it right underneath work energy theorem. That would make sense. F times delta x is equal to delta KE, the change in the kinetic energy. Last time, in the last couple of lectures, we focused on the kinetic energy part, right?
Yes.
This is the oomph that allowed you to do damage to stuff that was proportional to the velocity squared, right? And it's also the quantity that seemed to be conserved in addition to momentum when we talked about elastic collisions.
All right.
Today, we're going to focus on the work part, okay? Force times delta x. And so we'll start with a simple illustration. See if I can draw a nice picture here. There we go. And so, I guess I should make his legs longer. So that what has happened here, right, is that we have lifted this object by a distance delta x, right?
Yeah.
Our weightlifter here has lifted the weights up a distance delta x. Okay, so thinking about this work term, force times displacement, right? We see that our weightlifter here has exerted a force in the upward direction, right, in opposition to gravity, which is trying to pull this weight back down, right? And so the work that he's done will be equal to, he has to oppose the force of gravity. What's the force of gravity? It's the mass of whatever the weights are that he's picking up, right, times the acceleration from gravity, right?
Yes.
And we've done this times the displacement, delta x. Right? So here's the work that he did, mg times delta x.
All right.
So if this was, say, 100 kilograms, right? And gravitational acceleration is 10 meters per second squared, and he lifted this, let's say, 2 meters, right? How much work did he do? Well, we got 100 times 10, which is 1,000, times 2, which is equal to 2,000. And of course the question you have now are what are the units of it? Well, you could write kilograms meters squared per second squared, but we have a standard unit, right, where 1 kilogram meter squared per second squared is called a joule. Okay, and we'll learn about the guy after whom the joule is named later when we talk about thermodynamics. He is the guy that discovered the equivalence of heat and energy. And we'll talk about that later, but this one we write as 2,000 joules. Okay?
Okay.
That's just an example. Probably doesn't mean much to you to say 2,000 joules, okay?
Okay.
But when we start talking about different systems and their energetics, we'll likely use different units. So if we're talking about atoms, for example, we use a different unit of measurement called the electron volt, which just makes more sense to use. And we'll use joules predominantly when we do thermodynamics. But sometimes you use calories, which you've heard of, right? This is what they put on the label for food, which is really not a calorie. It's actually a kilocalorie, which is 1,000 calories. And that has to do with the heat that's released if you burn the food, which has something to do with the energy content that you take in if you were to eat that food. Another one we will use if we're talking about electrical power, right? The standard unit of energy there is the kilowatt hour. And we'll talk more about that when we talk about power later. But for now, just remember that the standard SI units for work is to joule. Okay?
Okay.
And if you use kilograms and you use meters and seconds, and then you're going to get joules as an answer. Okay?
Okay.
All right. The only other thing I want to point out on this is if I were to plot a graph of the force versus the displacement delta x, right?
Yep.
In this case, right, the force is mg, right? Mass times gravity, right?
Yeah.
because that's the weight of the weights, right? And that doesn't change in this case. And if I lift it over, because it's a constant when you're close to the surface of the Earth, right?
Yeah.
So the weight of those weights is a constant value. And actually this should just be x, and we'll say that our delta x is whatever our final position is. Let's say it's here, right? Then this minus the 0 would be the delta x, okay?
Okay.
And the work is actually the area under this curve, right? It's force times the displacement. Well, that is the area. And in this case, for a constant force, that's just the area of a rectangle, which is easy to calculate because it's mg times delta x, right? We
Yeah.
would have gotten 2,000 joules if we used mass of 100 kilograms and a displacement of 2 meters, right?
Yes.
If we went 4 meters, we'd get twice the amount, right? We'd have 4,000 joules, right?
Yes.
Also note, it's important to note that the force has to be directed in the direction of motion, okay?
Okay.
Here's just a question to see if we're on the same page here. What if I were to push a block across a frictionless surface, right?
Yeah.
I guess I should have drawn the block a little closer and make it look more like he's pushing. Right? Here we go. If I'm pushing this block across a frictionless surface, right, am I doing any work?
Now let me think. Let me just imagine it. No.
No, I'm not. There are no forces, right? If I'm picking it up, I do work, but if I'm just pushing it across a frictionless surface, there's no force that's opposed to me. If friction was there, I'd have to do work against friction, right? But since there's no friction, there's no work to be done, okay?
Okay.
And we'll talk more about the different types of forces in a minute. First, I want to do one more example, and that is a spring, right? So this would be gravity near the surface of the Earth, okay? Another system that we can consider is a spring, right? So this is the spring in its natural state, right? And this would be the spring in, let's say, a stretch state. There we go, right? I've stretched this spring a distance delta x. That's the displacement, right?
Yes.
So when I pull on that spring, right, the spring opposes me with a force which is equal to k times x, where k is just a spring constant that describes how tight the spring is. You can imagine you've got a loose spring that you can easily stretch like this, and then a tight spring that you really have to put some oomph into it to get it to move, right?
Yes.
That's what the k is, okay? So the work then, right, is going to be equal to the force times the displacement. But let's have a look at this, and actually I'm going to write this k delta x. I'm going to write this as k delta x, okay?
Okay.
But let's be careful here, right? Because let's do what we did before, and let's draw a graph of force versus displacement, okay? So the force is k delta x, right? So that is the equation of a line. Before we had a constant force, now we have the equation of a line. So if you don't have any displacement, you have no force, right?
Yeah.
And so you'll have a line where the slope of that line is, of course, k, right?
Yes.
And so if I have a displacement, let's say delta x, right? What is the area under this curve, right? At the full displacement, the force at this point is just k delta x, right?
All right.
Yeah? That's
Yeah.
the force I feel at this displacement delta x. And so the area under this curve, right, is the area of this triangle, right?
Yes.
The rectangle, k delta x times delta x, right, is twice the area of this triangle. So the work is 1/2 kx, or k delta x, but remember, if we multiply delta x times delta x, that's the same thing as delta x squared, right?
Yes.
Okay, so that factor of 1/2, right, is introduced into this because it's not a constant force, right, like it was before. Okay, so you have to be a little bit careful. Okay, does everyone understand that?
I think so.
Yeah. Because, right, I mean, as I'm stretching this spring out, the force is increasing, right?
Yes.
And so to say that it's just equal to kx times x, right, that doesn't quite work. Because it's the area under this curve of force versus distance, right? and the force is changing, okay?
Okay.
So these are the two basic systems that we'll work with in the next lecture and in the future in general, okay? We'll talk about other forces later, but these two are the ones we'll use for now. So springs, whose work is 1/2 k delta x squared, and gravity near the surface of the Earth, whose work is equal to mg times delta x, okay?
Okay.
Now in the case of gravity, right, if I lift the weight over my head, right, there's this potential that it's going to snap back. If I let go of that weight, what's going to happen? Fall on my head, right? If I stretch this spring out, right?
Yeah.
Right. Well, if I stretch it out like this, right? There is the potential for that spring to snap back, right?
Yeah.
Hit me in the face, right?
Yeah.
If I were to push a block across a table, right? So with friction, so not a frictionless surface like we've talked about in the past, but let's say it has friction. If I push a block across the table, right? I'm doing work on it for sure, right? But is there any chance that when I let go, that block is going to snap back and hit me?
No.
No, right?
Yes.
So this potential for something to happen, right, is kind of the origin of this term I'm about to introduce called potential energy. And so we call the work stored in the system, whether it's the weight that I'm lifting or it's the spring that I'm pulling back. You see how we're kind of storing this potential for something to happen into it,
Yes.
right? It doesn't happen when I push the block across the table because that's a different kind of force. And we distinguish between these different types of force by calling them conservative forces versus non-conservative forces. Okay? Conservative forces are those forces that have the potential to give back what you put into it. Okay?
Okay.
So like when I lift the weight above my head or when I stretch the spring out, right?
Yes.
And so the next definition I'm going to show, let me just erase this, is this idea of potential energy. And we'll call it delta U, and it's going to be equal to the negative of the work. Why the negative? Well, because as I lift the weight, right, I'm doing positive work on the weights, but gravity is doing negative work on it, right?
Yes.
And so that's kind of the origin of the negative sign. And we can be very... This exists for conservative forces, so I'll call this conservative work, right? So if I do work against a conservative force, right, let me just list some of the conservative forces. Gravity is a conservative force. Electricity, right, when we do electricity and magnetism, so electric forces, those are conservative forces. Springs, or elastic forces we would call them, are conservative forces. Things that are not conservative forces would be things like friction, right, or air resistance, right, or drag, right, when airplanes flying through the sky, the wind is hitting it, it's generating some heat, right, and that you cannot recover. So those are non-conservative forces, okay?
Okay.
And we'll talk more about how to define properly a conservative force later, but for now, let's just remember that distinction, okay?
Okay.
This means that we have to be able to get back the work that we put into the system. One thing to note, right, is this is a change in potential energy. There is no point, there is no absolute zero of potential energy, right? If I were to, for example, talk about the gravitational potential energy, right,
Yeah.
which would be minus mgh, the distance you lifted up, or minus mg delta x, right? If, let's say, I'm standing on a tiered structure like this, right, I could call this, you know, u naught equals 0, right, such that if I'm, like, for example, standing on the surface here, that would make sense, right?
Yeah.
This will be where I'm going to call my 0 relative to, and so if I lift a weight up to, say, this top height here, right, this distance, delta x, right, would correspond to the delta u, right? So this would be the u, and then u minus delta u. This distance here, if you want to think of it as a distance, would be the change in the potential energy. So where I define my 0 of potential energy is arbitrary, okay?
Okay.
If I'm standing on the second floor of a house, then I would choose where my feet stand as 0, and whatever I go up to relative to that, even though I might be, you know, 15 feet above the ground floor of the house, right? That doesn't matter. It's just the change in position will be the change in the potential energy, okay?
Okay.
What I want to look at now, though, are, so let's look at delta U for gravity, right? And this, right, remember is going to be mgh, right, or mg delta x. I'll just use delta x since we've been using that. mg delta x, right? So if I now graph delta U for the y-axis, and here's my x-axis, right? What does the graph of this look like? Well, it looks like this, right? It's a line. Okay?
Okay.
As I increase delta x, my gravitational potential goes up, right?
Yeah.
So it's 0 when delta x is 0, right? That's where I define my 0 for the potential energy. If I increase delta x, it's equal to, mass times acceleration, right?
Yes.
And so it goes up with this slope, mg, okay?
Okay.
So this is what the graph of it looks like. And the way to think about these potential energy surfaces is as follows. Think about if you were to place a ball on this surface. Think of it as a physical surface. What's going to happen to the ball?
That's going to start rolling.
It's going to roll down to here, right?
Yes.
So if you want to try to think about what are the dynamics of a system, if you can get a graph of its potential energy, right,
Yeah.
then you can get some idea of what the motion is going to look like. So in this case, it's just going to roll down to delta x equals 0. That means it's going to fall, right?
Yes.
Let's look at it for the spring, right? So delta u for the spring was equal to 1/2 kx squared, right?
Yes.
Well, that looks like a parabola, right? So if I were to graph delta u and x, right, I'm going to get a parabola. May not be the world's best parabola, but it is parabola-like. Let me try to do this side a little better. Okay. So if I want to think about what the motion of the system is going to look like, I just imagine putting a ball right here, right?
Yeah.
And let go. What's going to happen? That ball is going to roll down this hill, and then roll back up the hill, and then until it stops, and then it'll come back and back and back, right?
Yeah.
Okay.
Okay.
So what does that correspond to? So if this corresponded to things just falling, so a guy throwing a ball off of a cliff, right? Just going to go straight to the ground, right? What does this correspond to? Well, you can imagine. I'm not going to draw a picture of it, but if I take a spring and attach it to a fixed point, right, and put a mass on it and stretch it out and let go, what's going to happen? It's going to go. It's going to oscillate back and forth, right? Because remember, the spring, when you compress the spring, it stores potential energy again, right? We'll talk about this in the next lecture, and so it'll slow down until it stops, and then it'll push back out, right? So in and out, and it'll oscillate, right? This is oscillatory motion. It'll vibrate back and forth like this. If there's no friction and there's no loss in the spring, it'll do that forever, right?
Yeah.
So we can get a sense of what that motion is. If we see the potential energy surface, we can just imagine. Putting a ball in there, what's it going to do? This is what it's going to do. It's going to roll back and forth, okay?
Okay.
Whereas with the gravitational potential energy, it's just going to roll down and it's done. Stop, okay?
Okay.
So physically this corresponds to, objects falling to the ground, and physically this corresponds to, a vibrating or oscillating spring, okay? That's it.